we'll continue our discussion on receiver performance. So last time we saw how the SNR affects the bit error rate, right? And so continuing on that discussion. So optical receivers are characterized by something known as the sensitivity, okay, which is basically the minimum optical power required incident at my photodetector to obtain a BER of 10 to the minus 9. Right? So as we discussed last time, this 10 to the minus 9 is sort of like a benchmark that is kept for optical links. And so a receiver is more sensitive if it achieves this BER at a lower optical power, right? So, so the optical power typically we characterize as the average power. So you define the average received power as the average of the power received for bit 1 and bit 0. So we saw that there are two levels, right? And then we set some thresholds between them. So we'll characterize the performance in terms of the average power. So if, let's say for a long sequence, typically we have half the number of bits as 0 and half as 1. So the average optical power received is the average. Okay, so if you have a simple, what is known as IMDD, right? So intensity modulation direct detection. So bit 1 is transmitted with some optical power. Bit 0 is basically we don't transmit any optical power. And then we do direct detection at the photoreceiver. So the photocurrent is high for bit 1 and then low or close to 0 for bit 0. Right, so in that case, basically, we can say that P0 or equivalent the photocurrent for bit 0 is the mean current is sort of 0. Okay, so in that case, you can see that this average received power will just be half of the power for bit 1. Okay, and so the photocurrent detected for bit 1, okay, in general we can write like this, right? So including this multiplication factor. So if you have a pin detector, then M is equal to just 1. If you have an APD, then M will be some number, let's say between 10 and 50 or so, right? And then responsivity and then power received for bit 1. In terms of the average power received, it's a factor of 2 because of this relation here. Okay, if you look at the noise, so the standard deviation for bit 1, right? So that Gaussian at the upper level. So that will have contribution from the short noise, right? Because the power is or the photocurrent is non-zero, and of course thermal current, and so for the standard deviation we'll take the square root because these are variances, right? And for bit 0, since we don't have any optical power or photocurrent, then we only have the thermal noise current. Okay, and so we had already derived expressions for the short and thermal noise. So for the short noise, including this multiplication factor here, So this is the photocurrent right. So we included the factor m in general. So again, for APD you can take m equal to 1. Sorry, for pin photodiode you can take m equal to 1, and this was a function of m. Remember. So this FA will also be 1 for pin, but it will for APD it will be some higher value. Okay, so we've neglected the dark current here because basically we are saying that so for bit 1 the photocurrent I1 is much higher than the dark current. If you look at the thermal noise, recall that went like this: temperature and then load resistance, this amplifier noise factor, and the bandwidth of the detector. Okay, so to calculate the BER, basically we derived last time, right? It was some complementary error function of this Q factor, right? And the Q factor was defined as the difference in the currents between bit zeros and ones, right? So sort of like the signal level or the opening of the eye, right? Divided by the total noise, which is sigma 1 plus sigma 0. So in this case, again, I0 is 0 for IMDD. So this is just I1 in the numerator. Okay, and so with this expression you get, in terms of the average optical power received, so for sigma 1 we have short noise and thermal noise. Whereas for sigma 0 we just have thermal noise. Okay, so now we have expressions for the short noise and thermal noise current, which we can substitute here. And so the short noise term here also has is also dependent on the average optical power received. Okay. So what we can do is solve this equation, right? So again, recall that BER equal to 10 to the minus 9 corresponded to a Q factor of 6, right? So basically, when this Q factor becomes 6, so for the optical power at which the Q factor becomes 6, that is the sensitivity. Right? So basically, what we can do is solve this equation, take Q as a constant. So we have an optical power here in the numerator and also in the denominator for the short noise. So you can solve that. You get some sort of quadratic kind of equation because you have a square root here, right? But anyway, it's not straightforward to solve. So you get the average optical power that we need to receive for a given Q factor. Scales like this. Okay. So if you want to achieve a given Q factor, then basically from this equation we know how much power needs to be incident at the photodetector. Of course, for lower BER we need higher Q, which means we need higher power, right? So higher optical power received means we can achieve lower bit error rates. That makes sense. So let's look at this for the pin and EPD receivers now and compare. So for the pin photodetector, M is equal to 1, right? This FA is also equal to 1, the excess noise factor. And typically the thermal noise current will be bigger than the short noise current we saw because M is 1, right? So basically, so if M is 1, this is 1, this is 1, and this number typically is much smaller than this number. Basically saying the same thing again, that pin photo receivers typically operate in the thermal noise limit. Okay, so in that case, basically only the second term will survive or be dominant over the first term, and so the receiver sensitivity will just linearly scale with Q like that. Okay, so it's directly proportional to the thermal noise current and scales with Q. Okay, so if you have a larger thermal noise, then you need more optical power, of course. If the responsivity of the detector is smaller, then you need more optical power. Of that also makes sense. Okay, so if you put the formula for the thermal noise here, then you also see that the sensitivity scales with the square root of the receiver bandwidth, or equivalently the bit rate, right? Because typically, as we saw last time, the detector bandwidth is set proportional to the bit rate. Right? So you can see that the receiver sensitivity in the thermal noise limit scales with the square root of the bit rate. So as we go to higher data rates, we need more optical power at the receiver to maintain the same BER, and the scaling is as square root. Okay, so again, so delta F typically, let's say for example, is set at half the bit rate. So the 3 dB bandwidth of the receiver. So then basically the receiver sensitivity is proportional to square root of the bit rate. Okay, so if you put to look at some typical numbers, so if you take a typical InGas pin photo detector, the responsivity is about 1 amp per watt. The thermal noise current for a typical resistance, so as we discussed, typical load resistance values are between, let's say, 50 ohm to like a kilo ohm, in that range. And so for those load current values, typically the thermal noise current is about 100 nanoamps of that order of magnitude. So again, for BR 10 to the minus 9, we need Q equal to 6. So for Q equal to 6, if you substitute in this formula, the receiver sensitivity comes out to be about 0.6 watt microwatt, or 600 nanowatts. Okay, so you can see that's sort of the power levels we are talking about a microwatt that we need at the receiver, right? So if you use a standard pin photodiode as my receiver, then typically the powers that I need are about a microwatt, and with that, if my powers are about a microwatt or higher, I can achieve like 10 to the minus 9 bit rate operating in the thermal noise limit. Okay, so this is about minus 32 dBm. So 1 microwatt is about minus 30 dBm. Right? Okay, so now if we go to the APD, So for the APD, right? So if again, if we remain in the thermal noise limit, then you would expect the receiver sensitivity to be enhanced by a factor of m. That means you need a factor of m lower optical power, right, to get the same BER. But that doesn't happen because of this excess noise term also, because the short noise also increases for the APG. Right, and so recall that, so last time we had discussed that like we could have an optimum gain for the APD, right, such that the SNR, the electrical SNR that we get at the receiver is maximized, right? So we saw that first the SNR increased with the gain and then reached a peak and then started falling again. So there was an optimum gain that we needed depending on other parameters of the link, right? Similarly, we can calculate, so let's say our metric is 10 to the minus 9, we are here, right? So now we can say, okay, what is the optimum gain that I need? So recall this noise factor here depends on the gain, right? So I can say, okay, what is the optimal gain required for maximum receiver sensitivity or minimum this received optical power, right? So is there a value of m which will minimize the power that I need to get a BR 10 to minus 9? Okay. So I mean, it is similar, right? Last time we discussed basically an optimal gain for maximum SNR, right? Here, what we are saying is what is the optimum gain required for the SNR to be a particular value, right? Such that BR is 10 to the 9. And the optical power required to achieve that particular SNR is the lowest. Okay. So it's similar but slightly different. Basically what we are saying here is, so this expression for the receiver power required, that as a function of m, that we could use. Right, so for example, depending on the parameters, right, when you maximize the SNR, at that maximum SNR, your bit error rate could, for example, be, let's say, lower than 10 to the minus 9. It could be like 10 to the minus 10, 10 to the minus 11 at that maximum SNR, right? So if I'm okay with my link operating at 10 to the minus 9, then I don't really need that high SNR, right? Or equivalently for some other parameters, maybe at the maximum SNR, the BER doesn't even reach 10 to the minus 9, right? So the maximum SNR is one metric, but here what we are saying is let's say we want to operate the link at a particular error rate, and what is the optimal gain such that I require the minimum optical power to operate that link. Okay, so recall this was some function of m, right? Like you get something like this. Something like that. So anyway, if you substitute that expression and calculate this, you get the optimum gain value to be okay. So of course, it depends on this Ka factor, which is the ratio of this electron to hole impact ionization rates. Okay, and it's, you can see that as Q increases, your optimum gain is decreasing, right? So if you want to operate at a higher bit rate, sorry, a lower bit error rate, that means a high value of Q, right? That means actually your optimum gain is lower. So if you take again typical values of things here, basically this term turns out to be bigger than the other terms, so we can just write this as okay. So yeah, so you can say the optimum value of the gain goes down with increasing Q or decreasing bit error rate, right? Which is kind of counterintuitive, right? You would think that a higher gain would give you somehow a higher SNR and a lower bit rate, right? But we are seeing that the optimum gain actually is going down with increasing. Anyway, so if you put this value of M now here into this expression for the received power, that comes out to be okay. So if we compare to the receiver sensitivity for the pin photodetector, so you see here, one difference is that you can see that so for the pin photodetector, the power required scales as the square root of the bit rate, whereas here for the APD, you can see that the power required scales linearly with the bit rate. Okay. And if you compare the values typically, so let's say for the same Q value, so Q equal to 6, for example, let's say for 10 to the minus 9, for Q equal to 6, what is the received power that I need? So we estimated that for the pin photodetector here about a microwatt. You do the same here, let's say for the same bit rate for the APD here, okay, you'll get about so this value comes out to about 1/4 that for the pin photodetector for the same Q. So for the same bit error rate and the same data rate, we need about 1/4 of the power if you use an APD as compared to the pin. Okay, so that's the advantage that we are getting with using an APD, which gives me this multiplication. Right? But I have to use this optimum value of the gain. Right? It's not that if I just use higher gain, it will be better. Right? And that optimum value actually is, you can see here for lower and lower bit rates, the optimum value of the gain is smaller and smaller. Anyway, so so in terms of you can see that 1/4. So if you convert it to dB, this is like a 6 dB advantage, right? So I need 6 dB So in terms of dBm, so for example, for the APD, I will need about minus 38 dBm to get the same bit error rate. Okay, so this is known as the APD advantage. Okay, so the receiver sensitivity is better for the APD by about 6 dB, and the scaling with data rate is also different. It's linear compared to square root for the bill, which is basically a sign of short noise dominating here and thermal noise dominating. Okay, so sometimes we also so instead of the optical measuring the receiver sensitivity in terms of optical power, right? So in microwatts or dBm, sometimes we measure the receiver sensitivity in terms of like for example SNR that we discussed last time, or like number of photons per bit. Okay. So we just briefly sort of look at that. Nice. We'll keep this here. Look for IMDD. Okay, again, so let's go back to this Q factor. This was I1 minus I0 by sigma 1 plus sigma 0. So again, I0 is 0. So if you look at now again thermal noise limit, typically where we are when we use twin detectors. So in the thermal noise limit, basically thermal noise is dominant, which means if thermal noise dominates over short noise, then both sigma 1 and sigma 0 are just the thermal noise, right? So 1 also includes the short noise, but if thermal noise is dominant, then it's that. Right, so this means that the Q will be just I1 divided by 2 sigma, right? Because sigma 1 is equal to sigma naught. Okay, and then so we had discussed last time that this Q looks something like the square root of the SNR. Okay, so we can see that now more specifically here. So if we again define the SNR as so this is the electrical signal power divided by the electrical noise power. Right, so the signal power will be proportional to I square. Right, so I square times some load resistance, That will be the electrical power that we get for the signal. And the noise power will be proportional to the variance of the noise current. So that will be proportional to sigma 1 square, right? Variance of the noise. Okay, so from this expression for Q, you can see that the SNR is just comparing these two is 4 times Q square, right? So yeah, basically, as we discussed last time, Q is something like the square root of the SNR. Okay, so in the specifically in this IMDD case, we can see specifically that if you are in the thermal noise limit, then the SNR is 4 times Q squared. Okay, or Q is half of the square root of SNR. Right? So, for example, if you need again a bit error rate of 10 to the minus 9, we saw that that implies the Q of 6. Okay, from there we can see here that corresponds to an electrical SNR that we need from the photoreceiver of, so we put Q to 6 here of 144. Okay, so that's about 21.6 dB. Okay, so that's the kind of SNR we are talking about for bit error rates of 10 to the minus 9. Okay, for an IMDD link operating in the thermal noise limit, which is what we typically have if we use input. Okay, so we can also characterize this from by like the number of photons required per bit, right? So recall this I1 is like responsivity times power, and this one is like the number of photons in the bit times photon energy times bit rate. Right, so we can also relate this to the number of photons per bit required. And so for this SNR, it comes out to be, so the number of photons comes out to be like 1,000 or more. Okay. So I think we had discussed this briefly last time, in the last class also, through a different calculation, but yeah. So in terms of number of photons per bit, the receiver sensitivity turns out to be around 1,000 photons roughly for bit rate 10 to minus 9. Again, if you are operating the thermal noise limit with an IMDD link using a bit. So let's say if we were now operating the short noise limit, for example, by using an APD, then basically we are saying short noise is dominant, okay, and thermal noise is negligible. Okay, which means that so sigma 1 is given basically by the short noise, and that's much greater than the thermal current, so that's much bigger than the bit 0 noise, which is just thermal noise, right? So in other words, here sigma 1 plus sigma 0, I'm saying sigma 1 is much bigger than sigma 0. Okay. So Q here then is approximately I1 by sigma 1. Okay, now again compare it to the expression for the SNR, which is I1 square by sigma 1 square. So in this case, the Q is just square root of SNR. Okay, so in the thermal noise limit, the Q factor is a factor of half times the square root of SNR, whereas in the short noise limit, the Q comes out to be just directly square root of. Okay, so now you can see again, like for bit error rate 10 to the minus 9, Q is 6, and so this implies we need an SNR of about 36. Okay, which is about 15.6 dB. Okay, so you can see that if you were in the short noise limit, you could achieve the same bit error rate with a slightly lower SNR, right, compared to if you were in the thermal noise. Which is why we can use APDs in the first place, right? Because we saw that APDs actually worsen the noise, right? They give you higher gain, but actually the noise is enhanced by an even higher factor than the signal, right? So we saw that the SNR could actually degrade by using APDs, but we can still use them and get an advantage again, because why? Once we go into the short noise limit, right, then basically we see that we can achieve the same bit error rate at a lower SNR. And you can now see this roughly 6 dB advantage that we just discussed, right? So this is 15 dB, this is 21 dB, so that's like a 6 dB difference. Okay, in terms of the number of photons, so this expression we had derived last time, right? So we started from this expression. So for I1, this responsivity times the optical power, we wrote the optical power again like this, and then responsivity in terms of the quantum efficiency. Then we had this Q times divided by photon energy, right, which cancels out these terms. And then in terms of the photon number, we said that in the short noise limit, the SNR can just be written as the number of photons per bit. Right. Another way we said why this is coming out is, if you look at the SNR here, right? So we saw that for Poissonian statistics, the standard deviation goes as the square root of the mean, right? So if I1 is proportional to the photon number n, then sigma 1 is proportional to square root of n. So this term will be n squared divided by n. So I hope that is clear. Right. So from here, right, so basically what we are saying is the Q factor can be written in terms of the photon number as just the square root, and typically quantum efficiencies are 80-90%, we said, right? So this is roughly just the square root of the photon number, the Q the Q factor. And again, so recall the expression for the BER that we derived last time was this complementary error function of the Q factor. So if you put this, you basically get square root of the photon number. Okay, so this is the number of photons in bit 1, because in bit 0 we are not sending any photon, right? So again, if we put this 10 to the minus 9, then we get the number of photons required for 10 to the minus 9 to be about 36. So this is assuming your, let's say, quantum efficiency is close to 1. Okay. So again, if we compare it to the pin photodetector, the number here was like 1000 photons in my bit. Here we can see that if we are in the short noise limit, then we can achieve the same bit error rate, but now with much fewer photons per bit, right? Roughly a factor of 25 or so. Okay, so basically the summary of this discussion is that you can see that it is advantageous to operate in the short noise limit because you can achieve the same performance of the link in terms of the bit error rate with lower SNR or equivalently lower optical power detected at the receiver. Okay, and practically how we go into the short noise limit is by using a detector which has a high gain like an AP. Okay, so related to this sensitivity in terms of photon numbers, right? There is, so you can see that, so here we have computed the sensitivity in terms of photon number, right? And so the bit rates are not coming into the picture here, right? So you can see that for a given number of photons per bit, as I increase my bit rate, that means I need the same number of photons in a smaller time period, right? Which means my optical power has to go up, right? So that scaling still holds where I need higher optical power for higher data rates, right? It's just that if we look at in terms of photon numbers per bit, that is independent of the data rate. So talking about photon numbers, right? We can also look at what could be like the ultimate limit, right? So let's say we were somehow able to build ideal photodetectors. Okay. So these limits we are getting because of the noise mechanisms we have, right? Like thermal noise, short noise, in the photodetector. But let's say somehow somebody came up with some photodetector which eliminates all these noise sources. So then what is the ultimate limit on the receiver sensitivity, right? For example, you might think that in that case, if there is no noise, right, then for example, all I need is just 1 photon per bit, right? Because if there is no noise, I just detect that 1 photon. I say it's bit 1. If there is no photon, then I say it's bit 0, right? So for an ideal photodetector, will that be the case? So that is known as the quantum limit of photodetection, right? What is the best that one can hope for? Let's briefly just discuss that. There's a question. For high bit rate, we use pin photodiode. Yeah, so recall that the scaling, right? So the scaling that happens is sort of so for the pin photodiode, which operate in thermal noise limit, we saw this scale as the square root of the bit rate. Whereas for APDs, the sensitivity scales linearly with bit rate, right? So as I go to higher bit rates, you can see that the power I require for APDs is scaling much faster than for pin. So yeah, so basically this supports our discussion from last time that typically for very high data rates we would go back to using pin prototypes. But basically for a given link, like based on the parameters of the link, you want to compute this sensitivities for like pin APD in different limits, and then decide for that particular link which might work better for you. So this APD advantage, typically we're talking about, like, let's say data rates of about tens of gigabit per second, like 10, 20, maybe up to 40 gigabit per second. But once you go, if you want to go even beyond that, then first of all, as we saw, like to make APDs that fast itself is a challenge, right? Because this multiplication process is slow, it's not fast, right? So once you go to very high data rates, now let's say you're approaching 100 gigabit per second or something, then basically pin kind of photo detectors are the only way to go. Okay, so let's discuss this quantum limit of photo detection, which is basically the best that one can hope to do. Okay, and that is basically limited by these Poissonian statistics that we were talking about, right? So even in the best case scenario, we'll see that we can't go down to like 1 photon per bit required. We still need much more than that because of this Poissonian statistics that we're seeing, because of the discrete nature of electrons. Okay, so let's say you have some optical power incident here with some NP bar number of photons per bit. Okay. And let's say this NP number of photons generate, this is the average number of photons per bit, right? And it generates an average of m electrons, right? So these photons are absorbed in the photodetector, and you create electron hole pairs, right, which carry the current. So let's say for these number of photons, we get these number of electrons. So in the ideal case, for example, let's say 100% quantum efficiency, then every photon is absorbed to give an electron, right? Or more specifically, electron hole pairs. Okay, but the point here is that because of these Poissonian statistics, right, just from fundamental quantum mechanics, this number is not always constant. Okay, there is a spread. Right, so basically now we are averaging over 1 bit period and seeing how many electrons I'm getting in that time period. And the point is that that number is not constant. Okay. and it follows this Poissonian statistics that we discussed last time, right? So if you look at this value of m, so we measure it from many different bits. Sometimes we'll get a value this, sometimes we'll get a value of m which is low, sometimes we'll get a value of m which is high. Of course, we'll get some integers, right? And there will be some average value. And this distribution will be Poisson, right? Which means, so this distribution here is something like so e to the some average value, and then that average value is to the m divided by m factorial, right? So this is the Poissonian distribution. So this is the probability of getting m electrons. Okay, so the average value of m is this np. But I don't get np every time. Okay, and now when we are talking about the ultimate quantum limit of detection, then basically we cannot approximate this by a Gaussian anymore, right? So recall that if NP was much larger than 1, then we could basically what we were doing was approximating this by Gaussian and taking the noise as Gaussian. But now we're looking at how low NP can I detect, right? So basically I have to take the Poissonian statistics. I cannot approximate by Gaussian. Okay, so let's take an ideal detector, which means quantum efficiency of 1, right? So every photon which is detected is creating an electron hole pair. Also, no thermal noise. Okay, let's say no dark current. So ideal detector. But basically what we are saying here is that you will still have short noise, even for an ideal detector, because the short noise is coming from the discrete nature of the electrons, right? So even if you make your detector ideal, that doesn't change, right? So the discrete nature of the electrons still give you some noise, and that is the ultimate limit of the noise. Okay, so from this, basically for bit 0, since we are not sending any photons here, right? So for bit 0, there is no photons incident, and dark current is 0, thermal noise is 0, everything is 0. So the noise variance for bit 0 is actually just 0. Okay, which means that if I look at the bit stream now, right? So in the usual case, for example, when I have thermal noise, etc., it looks something like this, right? I have noise for bit 1 and also for bit 0 levels. But what we are saying here in this ideal detector case, the noise for the bit 0 is 0, which means this low level here actually looks correct. Okay. So for bit 0, there is no noise. The noise is only there for bit 1. Okay, so yeah, so this is some average current for bit 1, this is some average current for bit 0. So the current for bit 0 is 0, and also the noise is 0. Okay, so we saw that how, for example, in the usual case when we have noise here also, how do we set the threshold, right? We saw that to optimize the bit error, to minimize the bit error rate, we set this threshold which depends on I1, I0, and also sigma 1, sigma 0, the noises, right? So ID, the threshold came out to be something like sigma 0 I1 plus sigma 1 I0 divided by sigma 0 plus sigma 1. But in this case now, and we saw typically, let's say, for example, If you are in the thermal noise limit, you want to set that somewhere in the middle. But now here, you can see that the noise is only there for bit 1. Bit 0 has no noise. Okay, so actually, basically, you want to set your threshold as low as possible. Okay, as just very close to 0. And basically, what you want to do is you want to set this threshold corresponding to one photon, one detected photon. Okay, because we know that for bit 0, there are no photons, the noise is also 0, so there is no way I'm going to detect any photon for bit 0 in this ideal detector limit. So basically, if I just set my threshold at the level of one detected photon, then as soon as I cross that threshold, which means if I detect at least one photon, I can say it's bit 1. Okay. So that is the best way to set the threshold in this case, right? Because now this threshold will be furthest away from this average level. If I set, this is the minimum threshold I can set, right? One detected photon. I can't set 0 because then there is no threshold. So this way, this is furthest away from the one level where all the noise is. Okay, so in this limit of the ideal detector, I don't want to set the threshold somewhere in the middle or anything. I want to set it as low as possible, which is basically 1 photon. Okay, so basically, so if I set the threshold like this, right? So what are my errors now? So the probability that I detect bit 1 given bit 0 was sent. Right, so in this case, if bit 0 was sent, then basically what I am receiving is an ideal 0 with no noise, which means there is no way that I will detect even one photon, right? Which means basically, so this is the probability that I detect a current which is more than this threshold current value corresponding to one detected photon, given that 0 photons are received. Right, but in the ideal detector, you can see if the 0 photons are received, then 0 electrons are generated. So this is actually just 0, right? So just from here, for bit 0, I'm receiving absolutely like an ideal nothing, which means the probability of detecting one or more photons is 0. So I will not have any errors of this type where I mistake a bit 0 for bit 1. Okay, so but the other error, so if bit 1 was sent, but I detect it as bit 0, when will that happen? If the detected current is less than this ID, or basically it's 0, right? This is another way of saying that the detected current is basically just 0, because I've set the current at sort of the minimum level corresponding to one detected photon or one electron. Right, given some NP number of photons were sent. Right, so now what is this? This is non-zero, right? So now the distribution, so if some NP finite number of photons were sent for bit 1, then the distribution of the generated number of electrons looks like that. And here I am saying what is the probability that I detected 0 electrons. Okay, so this actually doesn't go to 0. Especially so when NP becomes small, right, once it starts approaching 0, it's not much bigger than 1, then this doesn't go down to 0. Which also shows you now that you cannot approximate this by Gaussian. Okay, so now I'm saying, okay, what is the probability that I get 0 electrons? So this is probability that m is 0, right? For an NP number of average. So that number we can compute by putting m equal to 0 here. Right? So that we can see that is just e to the minus np. Right? So this is e to the minus np. You can see that as np increases, this is e to the minus np. So this keeps going down towards 0 as np increases. Okay, so now again, the bit error rate is the average of the errors of this, that it detects given 0, and we detect 0 given 1% or detect 1 given 0%. And you saw this one of them is just 0, and the other one is just e to the minus np. So this is just e to the minus np by 2. Okay, so now so in this ideal detector limit, we've seen what is the ultimate limit on how the BER scales with the number of photons per bit given by quantum mechanics. So this is the best that we can do even with ideal detectors. Okay, so now this is a simple expression, right? So now again, if you put BER 10 to the minus 9, you get the number of photons in bit 1 to be about 20. Okay, so you can see that you can improve a little bit, but not by a whole lot. So just recall that we had just discussed that in the short noise limit, right, we can achieve BER 10 to the minus 9 with about 36 or let's say 40 photons per bit, right? We just haven't discussed that. And here what we are saying is that now if you somehow got an ideal detector, even with an ideal detector, you still need about 20 photons per bit. Okay, so you maybe improve by a factor of 2, but not more than that. So in other words, we are also saying that, for example, in the current links, when we are, for example, using APDs and detecting in the short noise limit, we are pretty close to the quantum limit, which is maybe quite surprising and also, yeah, I mean, worth appreciating. Is we are quite maybe a factor of 2 close to the quantum limit. Okay, so even if we somehow improve detectors a whole lot, we can't hope to improve the sensitivity by a whole lot. Right? That's the best we can do. So this is the number of photons in bit 1, right? So if we again take, like, let's say half the number of bits are 0 and half are 1, then the average number of photons per bit for the whole data stream would be 10. Okay, and then if we relate this to, for example, the average optical power received, which will be this average photon number times photon energy times bit rate. So again, if you take typical lambda 1.55 micron, bit rate 10 Gbps. So for this average photons of 10, you get the ultimate limit on the receiver sensitivity to be about 13 nanowatt. Okay, or in dBm, this is about minus 49 dBm. Okay, so that's the best you can do. Even with an ideal photodetector, the receiver sensitivity for a bit rate of 10 gigabit per second would be minus 49 dB. That much of power you will still need to get 10 to the minus 9 bit error rate. Okay, so yeah, I hope that's clear. Any questions? So yeah, so now basically we've discussed the noise mechanisms introduced due to the photo detection process, right, and how it limits our SNR and bit error rates um, for an optical link. Okay. But again, this whole discussion so far in the past 2-3 classes has been only the noise introduced due to the receivers. Okay. But of course, you could have other noise sources in your link apart from the receiver itself, right? For example, one case we already discussed is directly from your laser transmitter. Is you could have relative intensity noise. Right? Then we'll see that optical amplifiers along the link would also add their own noise. So these other noise sources which are apart from the receiver, right, will degrade your sensitivity, right? So this sensitivity discussions that we are doing are just from the noise introduced at the receiver. But if you include some other extra noise sources, right, that would degrade your sensitivity. Or in other words, for the same bit error rate, you would need a higher optical power than what we computed from here, if you include these other noise sources, right, because they will degrade my SNR. So we discussed a couple of important sources of this other types of noise. So there's a question: how did you compute average NP? That was just a factor of 2, right? So we're saying that for IMDD link, so if I'm sending 0 photons for bit 0 and NP for bit 1, then my average is the number of photons for bit 1 divided by 2. I just use that. Given for a long string, we have equal number of ones and zeros. Okay, so now basically what we're interested in is how the sensitivity degrades due to other noise factors, not from the receiver itself. Okay, so basically this is due to the noise in the incident optical signal itself, right? So far, basically, the noise mechanism we said was even if so we said that the optical power incident here has no noise. The photocurrent here is getting noise because of these mechanisms like short noise, thermal noise we discussed. But now you're saying, what if like there was some noise here in the incident optical signal itself, which typically will be the case, right? So that would further degrade my receiver sensitivity, which, or in other words, I'll need a higher optical power to, for example, operate at the same bit error rate. Okay, so this degradation is characterized by something known as power penalty. Okay, so this is the extra power that I need, the extra optical power that I need to get the same DER. For example, typically 10 to the 9. Right? So extra P over and above the minimum expected from just receiver noise. Right, so we just discussed how we compute the receiver sensitivity, taking into account the noise source at the receiver. But now, if we have some noise in my incident optical signal, then I need some extra power beyond that to get the same DER. Okay, and the extra power that is needed is typically what is called the power penalty. Right, so it's giving me how much basically sensitivity has degraded because of this extra noise, right? And so typically it's measured in dB, right? So you take 10 log 10 of the optical power required, including this noise, divided by the optical power required without this noise, just from the receiver. Okay, so we'll look at some typical sources which give us this power penalty. So, for example, first is a finite extinction ratio between the bit 0 and 1. Okay, so basically, for an IMDD link, so far what we've said is that for bit 0 we don't receive any power, and for bit 1 we receive some power, right? But so here basically my bit stream, so there is P0 and P1 for bit 0 and 1. So typically for IMDD or OK modulation, we are saying P0 is just 0. But there could be many factors because of which P0 is not exactly 0, right? One is, for example, again, just intensity noise from the laser, right? Even if I am turning it off, there is maybe some small power coming out. So, for example, when you turn off the laser below threshold, it's not completely off, right? Spontaneous emission is still on, and there is some LED-like emission going on, right? So, for example, that will be some finite P0 here. Then now I'm going through amplifiers. If I have a long link, I have some amplifiers, and they will add some noise for bit 0 also, right? So they will increase the bit 0 level above 0. And then finally, for example, if I have some intersymbol interference due to dispersion, right? So this pulses are broadening, and now if I have some intersymbol interference, you can see that, so now bit 0 won't go to 0 because of this intersymbol interference, right? So all these mechanisms can give me a finite extinction ratio where P0 is not 0. Right, so you can imagine that as this extinction ratio increases, my power penalty becomes worse. I need more and more power, right? Because now the distinction between 1 and 0, bit 1 and 0 is decreasing. So again, if you look at this factor of Q, that's this. I1 is responsivity times power in bit 1. I0 is T times power and bit 0. Now we are taking T0 not to be exactly 0. Again, average power received is the average of 1 and 0. Okay, so if you just plug these expressions here, we can get Q in terms of the average received power like this. Okay, so you can see now that Q depends on this extinction ratio for a given average received power. And you can see that as this extinction ratio goes up, Q goes down. Right? Worst case scenario being, so if your extinction ratio is 1, which means P0 is equal to P1, then you can't, bit 0 and bit 1 are the same. Q is 0, which means bit error rate is half, right? So that's just random. Because bit 1 and 0 look the same, you don't know which one is bit 0, which one is. So you pick half at random, half will be correct, half will be wrong. Okay? And the best case scenario is R equal to 0. Okay, so again, if we look, for example, in the thermal noise limit, operating with a photoreceiver, then noise for bit 1 and 0 are basically the thermal noise current. Okay, so basically I can write this received optical power in terms of the extinction ratio okay, and the Q factor like that. Okay, so we already saw the case for R equal to 0. So this factor was 1, right? And when we saw that the thermal noise limit, the receiver's sensitivity is scaled with Q linearly like that. But now when we have finite extinction ratio, you can see that for the same Q, I need a higher optical power by that factor, right? So if R is greater than 0, you can see that this factor is more than 1. So I need a higher optical power for the same Q, or for the same bit error rate, I need a higher optical power required, which is basically my sensitivity has degraded. Right, so the power penalty now, by this definition, how much extra power I require is basically just this much. So in dB, so power penalty due to finite extinction ratio is just 10 log 10 of this factor. Right, so if I plot this power penalty, as a function of this extinction ratio here, so it goes like that. Okay, so typically a figure of merit is we want to keep the power penalty below 1 dB. Okay, so basically we budgeted for a link and we say, okay, we need this much amount of optical power to operate at this data rate and this bit error rate, right? And so all these other extra factors we want to keep as small as possible. So typically, for example, you want to keep the power connected due to these extraneous sources below 1 dB. Okay, so if you want to do that from here, you can see that the extinction ratio has to be less than 0.1. Okay, so the amount of power you receive in bit 0 at max maybe can be 10% of the power received in bit 1. Okay. If you want to keep this power penalty lower than 1 dB. Okay, and just to give you some sense of numbers here. So when we typically, so this is the power current characteristics of laser, right? So if we typically, so for bit 0, we turn it off just below threshold, right? So once you go below threshold, typically this extinction ratio, you can make it sort of 5% or better. Okay? So typically you can achieve this by having the laser go below and above threshold. Okay, so this was for the thermal noise limit for pin photo receivers. If you go to APD receivers, then you have to take short noise also for the bit 1 noise. Okay, in that case, basically it makes it a little bit worse. So the curve shifts up. Okay, by roughly like it's about 3 dB. So typically the power penalty for APD is roughly like twice for the pin. So this goes up by 3 dB. But again, once you go to very small extinction ratios, then it starts to come together with the spin curve, and the power penalty can be kept below. So typically for APDs also, if your extinction ratio is less than 10%, then typically you can achieve this 1 dB less than 1. But in general, for any finite extinction ratio, this power penalty will be worse for the APD, because you can imagine now, so there will be some short noise for bit 0 also, because there is some power in bit 0. Okay, we'll stop here. So next time we'll discuss a couple more sources of the sensitivity degradation. And then wrap up sort of our discussion on optical receivers before moving on to optical amplifiers, which is the next topic.